Hello. In this video, we introduce a special type of function that's actually related to the last one that we studied, the exponential function. This is its inverse. It's called the logarithm. So let's take a look at logarithmic functions and things that grow a lot more slowly than exponential. So we begin by reminding ourselves what an inverse function does. Inverses, by definition, undo operations. For example, the inverse of addition is subtraction. The inverse of multiplication is division. We also talked about how we can insert one function inside of another called function composition, and if they undo each other, if f undoes g and g undoes f, then the f and g would be called inverse functions. Today we introduce the logarithmic function. So take a look with me at what we mean by the logarithmic function here. We say exponential and logarithmic functions are truly inverses of each other, meaning that they undo one another. But that would also mean that if I was going to define a logarithm, I need to understand what that means. When we think of an exponential function, for example, this situation, b to the y equals x, I can claim that is exponential because I have a variable in the exponent. But if I wanted the inverse of that, I would need to switch x and y. So I would now have b to the x equals y. We talked about how to find the inverse function in a previous video, so you can go back and watch the inverse function video if you need to. So if we had b to the x equals y, we can actually rewrite that as a logarithm. The way we do it is we write y equals log base b of x. So all we do is we take our base that we had previously in our exponential, here is our base, and we now make it the base of our logarithm. So it's like a subscript, it's smaller font below. So we have logarithm base b, and then what we notice is that the way we go back and forth from exponential to logarithmic is whatever the exponent was of the logarithm, that's going to go on the other side of the equal sign here. So this will be read b to the y equals x. So the x that we had here, the non-exponential part, that is our argument of our logarithm. So the way you read the logarithm is y equals log base b of x. Log base b of x. Now you might be wondering, could I have any base for a logarithm? The answer is no. There are certain bases which were not allowed for exponential functions. For example, if we had exponential growth, we might be doubling every time, like 2 to the x, y equals 2 to the x, so you have a base that is positive 2. On the other hand, you could be cutting in half every time, like a base of 1/2. 1/2 times 1/2 times 1/2, so y equals 1/2 to the x, another base that's positive, but between 0 and 1. Could I ever have an exponential base which was negative though? Like -2 times -2 times -2? Well, yes, you can multiply a negative number by itself over and over again, but would that show exponential growth or decay? Would I be continuously growing or falling? No, because the signs would keep changing, wouldn't they? You'd go from positive to negative to positive to negative. You wouldn't have steady growth or decay. That's why we claimed in our previous video on exponential functions that the base had to be non-negative. It had to be bigger than 0. It also had to be bigger than 1, or not equal to 1, I should say. It could be between 0 and 1. But if it was equal to 1, 1 to the x would be 1 times itself over and over again. Are you growing if you just keep getting an answer of 1? Are you decaying if you keep getting an answer of 1? No. So we have a couple of restrictions on the base for an exponential. Namely, it cannot be negative and it must not be 1. Okay, if that was the restriction on the base of the exponential, that's also the restriction on the base of the logarithm. So the same thing applies here. The base of my logarithm can be any number as long as it's not negative and it's not equal to 1. With that in mind, how do I go back and forth? Here we go one more time. Your base to your power equals your argument. So in this case, b to the y equals x. And then if I were to switch x and y, I would get back to my original y equals b to the x. I would have two inverse functions which we'll graph side by side in a few moments. One grows quickly, one grows slowly. So some things to remember as you're playing with logarithms. If you have a scientific or graphing calculator, there is a logarithm button on those calculators. They're either going to be the log button, which is base 10. We call that the common logarithm. Or it's going to be the ln button, which is base e. We call that the natural logarithm. Okay? So if I have base e, that is going to be represented by, instead of saying log base e, we'll just write ln for natural log. Some students wish it was NL because natural log makes sense, but it comes from Latin where they put the adjective before the noun, or vice versa rather. I said it backwards there, but you get the idea, I hope. So natural logarithm will be written as ln, and that means I have a base of e, where e is approximately 2.71. It's that irrational constant, kind of like pi, that goes on forever without a certain pattern that we know about. We know how to approximate it, but we don't know the exact value. So we say that would be our base e. Okay, so if I see log of x, I think base 10. If I see ln of x, I think base e. So keep those in mind. You can use both of them at different times depending on the word problem you're dealing with. They have different times where one is more beneficial than the other, but in general, when I say take a logarithm of any of both sides, you can pick any base as long as it's not negative and it's not 1. Let's go ahead and practice, if you understand the concept that I mentioned in the middle of the slide, how to switch between logarithmic and exponential form. Suppose you have log base 3 of x equals 2. How would I switch this to an exponential equation that says the same thing? Where would I start? Good, with my base. So my base to my power equals my argument. So in this case, you would write 3 to the power of 2 equals x. Now we've said the same thing, but instead of using logarithmic lingo, we're using exponential lingo. So this tells us the answer is just x is 9, right? 3 squared is 9. So when someone says log base 3 of what number gives me 2, the answer for x, that input, that argument, would be 9. So we'll have some shortcuts for how to handle logarithms. This is one of them, switching back to exponential form. You might be wondering, why would I use logarithms to begin with? It has to do with growth and its growth rate. So if a certain data set, for example, if you're talking about an earthquake in the Richter scale, the relationship between the magnitude of that earthquake and the actual intensity of the earthquake that you feel, that's going to be logarithmic in nature. It's going to be growing slowly. Similarly, if you're talking about loudness, so the decibels that you hear something, the loudness has to do with your frequency, and that's also a logarithmic relationship. Okay, so let's take a look at our next slide where we apply some of these properties. It says, can you switch between exponential and logarithmic forms? In A, it says 3 to the x equals 4.6. All right. So 3 to the x equals 4.6. Which type of situation do I have in front of me? Is this exponential, linear, quadratic, cubic, logarithmic? What is this? Got to know what kind of equation you're dealing with. This is exponential. If that's what you said, you are correct. And that's because your variable is in the exponent. So it's really saying multiply 3 over and over again, x times, and you should get 4.6. That's what this says. So if you were trying to solve for what x would be, one approach would be to rewrite this as a logarithm. So let's go ahead and do that. Let's practice rewriting it as a logarithm. So I would start with maybe writing log, and I would input my base. That's the easiest part. What is the base of the original exponential equation? That's right, it was base 3. So I would input my base right there. Then I would say, okay, the way that we did this, we said, was base to my power equals my argument. Base to my power equals my argument. You might want to write that in your notes. Base to my power equals my argument. So if the base was 3, what was the power? That's right, the power was x. So we're going to say 3 to the power of x equals my argument. And what is my argument in this case? The argument is, that's right, going to have to be 4.6. There. So this is saying log base 3 of the number 4.6 equals x. What that's really saying is x is the exponent, right? It's saying 3 to what exponent gives me 4.6. So if you cover up the right-hand side, if you cover up the x in that equation, what does log base 3 of 4.6 mean? Right? Probably nothing right now to you. It means it's asking the reader what or which exponent would work for 3. So if I raised 3 to some exponent, what would it be so that I'd end up with the result of 4.6? Earlier we had log base 3 of 9, right? 3 to the 2 equals 9, so the answer would be 2 there. So it just depends. If we can see it obviously, that's great, but most of the time we're going to need technology to help us get this approximation. So this answers this first question. Log base 3 of 4.6 equals x is means the same thing as 3 to the x equals 4.6. Right now we're just having you translate back and forth between the two versions. Try B on your own. Go ahead and pause the video. What is log base 3 of 1 over 9 equals negative 2? What is that in exponential form? Go ahead and try it. Okay, let's see how you did. Hopefully you tried it yourself. Well, we would start off by saying, what is our base here, right? Our base was 3. So we're going to have 3 to our power equals our argument, right? 3 to our power equals our argument. That's what this says. 3 to our power equals our argument. So what is our power here this time? Yeah, our power has to be negative 2. There he is. So 3 to the negative 2 should equal our argument. So what would our argument be this time? It would be 1 over 9, wouldn't it? So this should equal 1 over 9. Now, do you agree with that? Is that a true statement or a false statement? Let's think about it. That's the answer, right? But can we check if it makes sense? What does it mean to have a negative exponent? It means the reciprocal. Good. So that means 1 over 3 to the positive 2, doesn't it? Does that equal 1 over 9? Well, yeah, because 3 squared is 3 times 3, which is 9. So yes, this makes sense. We have translated it correctly. Okay, so you will want to practice this. Can I go confidently and competently? Can I go back and forth between exponential and logarithmic forms? This will be very important when I start solving real-life applications that need logarithms or exponents. Okay, so let's head over to the graphs. So we mentioned that logarithms and exponential functions are inverses of each other. They undo each other. But we also learned in a previous video on inverse functions that if you have two inverse functions, their graph should have a high degree of symmetry along the line y equals x. So if I were to fold the graph over on that line, y equals 1x plus 0, y equals x, I should have a mirror image, meaning that every point on both sides of that line are the same distance away. So that's a nice way to visualize what the situation is. Also, if I'm an inverse function, we've learned that your x values and your y values have been switched. In other words, the domain of one is the range of the other, and vice versa. So that's the first point that you notice here. The domain of your exponential function equals the range of your inverse function, which is the logarithm. Okay, and vice versa. The range of the exponential function is the domain of the logarithmic function. Now let's take a look at the graph. We already mentioned the symmetry along that line y equals x. But if I wanted to sketch the graph of two inverse functions, one is exponential, one is logarithmic, we need to remember the three key points from our exponential functions. So maybe we can do an example as we go through this one. Let's take a look at the exponential first, the one that should be familiar to you. So for example, suppose I have y equals 2 to the x. Would you agree that that's an exponential equation? Good. Where the base is 2, so did that mean I'm growing or decaying? Growth. Good job. If the base is bigger than 1, it's growth. If it's between 0 and 1, it's decay. So I'm doubling each time that x increases. Okay, so now I notice that my key points, hopefully you remember, my key points for this exponential function were, when x is -1, what happened? We got the reciprocal, right, of the base. So 1 over the base. That's what we're saying here. 1 over my base. So what is the reciprocal of 2? Well, that's 1/2. This is because 2 to the -1 is 1/2. The other points that we got were when x was 0. 2 to the 0 power is 1. So remember that 0, 1 was always on the graph of an exponential curve, b to the x. And then we had when x is +1. 2 to the 1 is just the base itself, in this case 2. And so we always get 1 giving us our base when we have b to the x. And we also had a horizontal asymptote, meaning that as we go to the left and right extremes, our y values get closer and closer to 0, right? Okay, so we had that situation. Now let's take a look at what that looks like on our graph here. So that was y equals 0 there. That would mean that on our graph here, we had a point at 0, 1, but we would also have a point at -1, 1/2. So that would be around there. We would also have a point at +1 and maybe 2's here, right here. So something like that is going on for our graph y equals 2 to the x. But on the other hand, so we could talk about domain and range, we'll come back to it. If I wanted its inverse function, I would need to switch x and y, wouldn't I? I would have x equals 2 to the y. But then I could write that as a logarithm. I encourage you to pause the video and try it. If you have x equals 2 to the y, write that as a logarithm. What would you have? Wouldn't it be y equals log base 2 of x? See if that makes sense if you switch it back. 2 to the y equals x. Yeah, so that is what would happen if I switched x and y. So that would mean that if it's truly switching x and y, that my new points, instead of at -1 and the reciprocal of my base, I would have the reciprocal of my base, so 1 over b, and then -1. So my first point would have, instead of an input of -1, an output of -1. And its input would then be 1 over 2. The reciprocal of 2 is 1/2. So that's what we notice right there, that the first point to memorize for log base b of x is the reciprocal of your base, or 1 over b, comma, -1. Similarly, if I switch your x and my x and my y for the point 0, 1, now I would have the point 1, 0. Okay, so that means that log base 2 of 1 gives me 0. We'll think about that in a few minutes. And similarly, if I insert 2, my base, I should get 1. So all I'm doing is switching x and y. Hopefully you can see that. Instead of a horizontal asymptote at y equals 0, I should get a vertical asymptote at x equals 0. A lot of students still struggle with the fact that a vertical line is x equals a number and a horizontal line is y equals a number. Please make sure that you become a master of that concept, because if it keeps becoming an issue, it's going to carry on into your future math classes, and that will cause problems in your understanding, especially when you get into 3 dimensions in calculus and you're rotating things about lines. You need to know which one's which. So a horizontal line y equals 0 is our asymptote for exponential growth or decay, and the vertical line x equals 0 is our vertical asymptote for the logarithmic function. So that would be what I write here. My vertical asymptote is x equals 0. So let's go to the graph and see where those points might be. We have 1/2, -1, so maybe that's here. We have 1, 0, that looks like there. And we have 2, 1, so maybe 2, 1 right there. It does appear that those points are mirror images about the line y equals x. So there's our line y equals x. So we should have a mirror image about that line, same distance away from that line. Now let's look at our domain and our range for a moment. For the domain of the exponential, notice we could insert any exponent for x, couldn't we? X could be any negative value going to the left forever. It could also be any positive value. So the domain for the exponential was all real numbers, -∞, comma, infinity. But wouldn't that also then be the range of my problem here? So it should also be -∞ to infinity. Why would that be the range of my logarithm? Well, look at the red logarithmic curve. Isn't it going down forever and slowly up forever? It does look like that. So it is true that switching the x and the y's to get my inverse graph will mean that the domain and the range have swapped. What about the range of my exponential function? The range of my exponential function. Look at that blue curve. Oops, I didn't mean to do that part. Let's see if I can get that eraser. Okay, look at that blue curve. What do you think the range of that blue curve would have been? Y equals 2 to the x. How low can it go? It goes closer and closer to 0, right, as it goes left forever. So the lowest y value would be right above 0. So parentheses, meaning I don't include 0, toward infinity. It goes up forever. Why does it not include 0? Well, think about what's happening as you go left forever. You get 1/2, you get 1/4, you get 1/8. You continue to chop in half. You get closer and closer to 0, but you never actually reach 0 by cutting something in half infinitely many times. You just get closer and closer to it. On the other hand, that would also mean then that if the domain and the range have swapped, that the domain of the logarithmic function would also be 0 to infinity. That's a really important point. That means that the inputs, the x values for this logarithmic red curve, those x values must always be bigger than 0. That means that if I was solving a logarithmic equation, like we'll do in our next video, when we get to solving logarithmic and exponential equations, one thing you'll have to worry about is if you get an answer like x equals -5 as your possible input that might work, that would not work in this case because x has to be greater than 0. Otherwise, it's not a defined function. It doesn't make any sense. So keep that in mind. That will affect our domain of logarithms. So this is the most important takeaway, besides the basic graphs, about domain. You need to remember the domain of a logarithmic function is always x values bigger than 0 if it's just y equals some base, log base b of x. Okay, so what you will need to do is memorize the 3 key points for both the exponential and the logarithmic function, and then be willing and able to move these graphs around based on our transformation rules from our previous studies, moving them left and right, up and down, and shifting and stretching and shrinking and all of those fun things. So make sure you practice those transformation rules if they're rusty from our previous chapters, but also memorize these 3 key points and the basic structure of what you expect the graph to look like if it's growing or if it's falling. So I didn't talk much about the falling case. It's the same exact points, except for instead of growth, you see decay. One is decaying rapidly, that's exponential decay, like half-life and populations like such. And then the other is decaying very slowly. That's logarithmic decay. All right, so let's head over to our next slide where we try to graph these by ourselves. It says analyze and sketch the graph of the inverse functions below. F of x equals 1/3 to the x power. Now, which type of function is that? All the functions we've studied in the course, which type of function is this? If you said exponential, you are correct. And the reason I know this is exponential is because x is in the exponent. Good job. So the first thing I would recommend is to remember the 3 key points and the basic structure of the graph. For an exponential graph, it's quickly growing or falling. Is this one growth or is this one decay? Based on your base, right? This one would be, in fact, decaying. So this is exponential decay because our base b is 1/3, which is between 0 and 1. In other words, you're dividing by 3 for every increasing x value to get your new output. So what were our 3 key points? You go ahead and pause the video and see if you can figure them out yourself. And what was your asymptote? Okay, let's see what you got. Did you get -1, the reciprocal of 1/3? 1 over b would be 1 over 1/3, or just 3 over 1, which is 3. Good job. That one's kind of tricky for students. Did you get 0, 1? When x is 0, anything raised to the 0 power is 1. Good job. What about an input of 1? 1/3 to the first power is 1/3. Good job. So you just got your base. And what is the horizontal asymptote for any b to the x exponential function? That's right. As I go to the left forever or the right forever, I should be approaching 0. So with that in mind, and remembering that this was exponential decay, I'm expecting something like that to happen. So I go to my graph and I plot those points. I'll pick a darker color so you can see. How about -1? That'd be here. And then up 3. 1, 2, 3. Okay. How about 0 and 1? That looks like there. And how about 1 and 1/3? Maybe around here. So it would appear, if I were to graph just a quick sketch, that I have exponential decay taking place here, getting closer and closer to 0 as I approach the right forever. Okay, and I could even show that horizontal asymptote if I wanted to show off here. As I get closer and closer to 0, to the right, I should say, I get closer and closer to 0. So this would be my horizontal asymptote, y equals 0, for the exponential graph. Okay, so we've plotted the exponential version. Maybe that's what you got, I hope so. And on my graph, if you're doing this in-class test, make sure that you label your points and your asymptote correctly. Okay, try the logarithmic version of this same function, same base, but now it's not exponential, but logarithmic. Go ahead and pause the video and see if you can do it. Okay, did you get as your 3 key points, switching x and y, 3, -1, 1, 0, and 1/3, 1, with a vertical asymptote at x equals 0. Nice job. If you did, those would be the 3 key points that I would recommend using to do a sketch, right? You could have picked other points. Sometimes on tests, students pick random points, but I need to see that you've understood how the graph moved. If there had been a transformation, left or right, up or down, you would need to show me that you have moved according to those rules, okay? Now you notice that this one is not exponential decay, but rather logarithmic decay. So that should be looking something like this. So we keep in mind the basic idea, and now we'll simply put our points on the graph. So we have a point at 3, -1, so 1, 2, 3, down 1 unit, so that would be around here. We have a point at 1, 0, that would be around here. And we have a point at 1/3, 1, so 1/3 and then up 1, around here. So if I was to graph this, remembering that I have a vertical asymptote this time, let's pick another color that might be seen here. How about purple? My vertical asymptote is x equals 0. So on the graph, that would be this line on the y-axis. So that's x equals 0, my vertical asymptote. So I should be getting closer and closer to that asymptote as my logarithmic curve is going towards 0. So let's take a look. Toward the left, it gets closer and closer to that number 0 and going this way. So this graph continues. You could continue showing the graph. I definitely cut it off early. But what I'd like you to see as it gets closer and closer, it's going like this. Okay. What I would like you to see is the nice symmetry that you should be noticing as these graphs get closer and closer. There should be symmetry along which line? That's right, the line y equals x. So the line y equals x is always that marker of symmetry. You should be the same distance away from each direction to that line. Okay. All right, so the final 3 key points, you can see them labeled above. The asymptotes were also labeled above. The domain and the range of each, let's talk briefly about those. What would be the domain of f? What would be my domain of my exponential function? Yeah, you're right. It would be all real numbers. Good job. What would be my range of f? Yep, it would be above 0, it looks like. So parentheses 0 to infinity. Good job. And now let's do the domain and range. You should have the answers right in front of you now. What would be the domain of g? Can you think of it? Well, it should be the same as the range of f. Is it 0 to infinity? Check it out. Can you be any x value that's to the right of 0? Yeah, you can. It makes sense in the graph. And how about the range of g? What should it be? It should be the domain of f, right? All real numbers. So if you said negative infinity to infinity, that would make sense because you can see the red curve is going down forever slowly and up forever slowly. So negative infinity to infinity makes sense. Okay. So now imagine doing a lot of these graphs, not just until you can get one of them right like an amateur, but until you can't get any of them wrong like a professional. So you're going to try to make sure you practice your graphing skills over and over again until you become an expert. But there's one more thing we need to talk about in this video besides graphing. We need to talk about domain real briefly. The domain of a logarithmic function, we've mentioned it already, is such that in your original graph, y equals log base b, so any base, x. Prior to transformations, we said that graph, if it's growing, if b is greater than 1, let's say, if it's growing, it looks like this, right? The last example, it was decaying, so it went the other way. If that's the case, what was my domain in that picture? It was any value to the right of 0, right? But what if we've moved that graph? And you're going to get practice with that in your online homework, right? If you've moved that graph, for example, if I have y equals log base 3 of x minus 8, how would that graph have moved with that transformation x minus 8 in parentheses? Think back to your transformation days. This moves it left, right, up, down. How does it do it? It moves it left or right. Good job. And it's counterintuitive, isn't it? So it's actually moving it to the right 8 units. You can go back to your notes if you need to remind yourself of that or the old videos. So right 8 units, that would mean my graph, instead of having the asymptote at 0, where do you think the asymptote is now? Yeah, it would be at 8, wouldn't it? So this is x equals 8, and then the graph would go like that, wouldn't it? So if the graph is shifted over 8 units, the asymptote 0 has also shifted over 8 units. What would that mean for my new domain for this function, right? My domain would be any value which is to the right of 8. So 8 toward infinity. I know that kind of looks funky. The infinity symbol looks like an 8 on its side, right? But that's saying any value bigger than 8 would be allowed for x as an input. So in other words, what is a shortcut? If instead of having to think about the graph every time, we call the argument of the logarithm here x minus 8. So all I really need to do is say my argument originally was x, right? And I said x had to be greater than 0. Now the argument is x minus 8. So my argument, x minus 8, must be bigger than 0. If you simply set your argument, like I wrote down here, up here rather, if you set your argument greater than 0 and solve for x, you will know your domain instantaneously. So what is our domain? X, adding 8 to both sides, x must be greater than 8. And that means the same thing as interval notation, parentheses 8, comma, infinity, close parentheses. Okay, let's have you try one on your own. In example 3, it says, could you find the domain of this logarithmic function? H of x equals 8 plus 5 times the natural logarithm of 2x plus 3. Wow, there's a lot of transformations going on here. One that we haven't even talked about in this course, which is a compression horizontally. You'll learn about that if you take trigonometry. So we had that compression. We have a horizontal shift, moving it to the left or right. In this case, it would move it to the left. We also have a stretch, multiplying the y values by 5, so it's growing a little bit faster. And then we have plus 8 at the very end. Usually we would have written that on the right at the very end, but that just means move the whole graph up 8 units at the end. So there were 4 transformations that you could have done if you wanted to graph this by hand. But we don't even need to do that. What do we need to do to find just the domain of a logarithmic function? Feel free to pause the video and use your notes to answer this question. To find the domain, we set the argument greater than 0. Now in this course, you've probably heard about 2 other types of domain restrictions. Denominators can never equal 0, good, and under a square root, you can never have a negative. So you would set your radicand, whatever's under the square root, greater than or equal to 0. But with logarithms, the new restriction for us is whatever the argument is of your logarithm, no matter what the base is, base b, base e, base 10, base 5, whatever that base is, the argument can never be 0 and it can never be negative. So I take 2x plus 3 and say it must be bigger than 0. This will tell me the appropriate x values for inputs for this function to truly exist. Solving that, did you get 2x is greater than negative 3, so that x must be greater than negative 3 over 2? If you did, let's see if that makes sense. If you input negative 3 halves itself right here, you would have 2 times negative 3 over 2. The 2's cancel and you'd have negative 3 plus 3, which is 0. So I can't have that because I can't have a 0. I also can't have anything less than that because that would be negative. So I must have something bigger, and that's where it makes sense. Any x value that is bigger than negative 3 halves would work. You might be thinking, I thought I couldn't have a negative in there. You can have a negative for x as long as the entire argument is not negative. So for example, if I had a negative 1, would that be okay? If x equaled negative 1? Well, negative 1 is to the right or bigger than negative 1 and a half, which is what we have here. So input negative 1 and see what happens. 2 times negative 1 is negative 2. And if you add negative 2 to a positive 3, you get a positive 1, which we're allowed to have. So this would be an appropriate x value because it is a value bigger than negative 3 halves. Okay, so the domain I would officially write as parentheses negative 3 over 2, comma, infinity. If that's what you wrote on your paper or you were thinking of writing, good job. All right, we have one more example. Let's head over to some log properties before we call this video a day. It says simplify with these logarithmic properties. Log base a of 1 equals 0, log base a of a equals 1, and log base a of a to the r equals r. I suggest that you memorize these 3. They're going to be so common, they will save you time. Otherwise, you have to rethink about it every single time. So let me show you what I mean about the first one. This says no matter what your base is, you could have put b, a, anything you like. If you have an argument of 1, the answer will always be 0. Why is that? We'll do the process here. Switch it back. This would say a to the 0 equals what number? Well, anytime you have a 0 exponent, which is what this is an exponent. Logarithms are just exponents. Anytime you have an exponent of 0, the answer will be 1, won't it? So that makes perfect sense. So if I see an argument of 1, that's saying the answer turns out to be 1, that must have been that the exponent was a 0. Okay, so let's try another one. Why does the next one make sense? This one's saying if your argument and your base are matching, the answer is 1. The exponent is 1. Well, that's saying if you switch it back to exponential, a to the 1 equals what number? A to the 1 would have to equal the base itself, a. Right? That's the only way you can multiply something by something that's the same thing and get itself. You must have just multiplied it by itself. It was just a one time. There was no other copies of a present. Otherwise, you would have had a squared or a cubed, etc. So if you're getting back to a, the exponent had to be 1, meaning you just had one copy of that thing. Notice the last one here. If I have a as my base and a to the r as my exponent, right, the answer has to just be the exponent. So if your base and your argument match, but there's an exponent there, the answer is just your exponent. You can see why that happens. Switch again, you'd have a to the r equals what? Well, it has to equal a to the r. So that means that these have to match. That's the only way that would work. So see if you can now by yourself pause the video and apply one of these properties to a, b, and c. Okay, let's see how you did. In a, it says we have log base 2 of 2. So which of these properties am I applying here? If you said the second one, you are correct. The base and the argument matched, so the answer is just 1. Can you see that it works? Is 2 to the 1 equal to 2? Yes, so that makes sense. The next one, B, might have been a little trickier for students. What's happening here? Well, if it's an ln, what is the implied base? That's right, it's logarithm whose base is e. So you might need to write it out until it makes sense to you. Now do you see that they match the base and the argument? So what is this answer? Same property, it's 1. And notice if this had been ln e to a power, the answer would just be that power. Try C now. What's happening in C? So I have log base 5. Could I write the cube root of 25 as 25 to some power called a rational exponent? Yeah, wouldn't that just be 25 to the 1 over 3? I could do that. You could have also said 25 is really what number squared? It's 5 squared. Good job. So isn't this really log base 5 of 5 squared to the 1/3? Oh, that's kind of tricky, isn't it? Because 5 squared is 25, and I'm raising it to the 1/3. Well, this is getting interesting. I almost have the same base and the same base raised to a power, but I need to remember a power rule. Do I remember, let's go over here for a moment, that if I have b to some power, and I raise the whole thing to another power, it's saying take this many copies of b to the m. What happens? That's right, I get b to the m times n. If you're wondering when I add, that would be if I had b to the m times b to the n. That's when I multiply the same bases, I add the exponents. But if I have a base to a power multiplied or raised to another power, I just multiply the exponents. So this becomes logarithm base 5 of 5 to the 2 times 1/3. What is 2 times 1/3? Well, that's 2 over 1 times 1 over 3, which is 2 over 3. So we have this. That's what happened up here. Little think bubble. Okay. So what is the answer now? If I recognize that this is really that third rule, the third trick, same base, same argument, raised to a power. What is the answer? It is 2/3. Good job. So this is telling me that 5 to the 2/3 means the same thing as the cube root of 25. You could put both in your calculator, you'll get exactly the same answer. They mean the same thing. Okay, so really make sure you understand the difference between an exponential curve and a logarithmic curve. One is growing or decaying slowly, one is growing or decaying quickly. Also memorize those key points and these properties before you see me in the next video where we build on this knowledge. Remember to practice because math is not a spectator sport. I'll see you next time.